All right, kiddos, welcome back. This is our part 2 to our measurement and data notes, and today we're going to talk about scientific notation and types of models. So we're going to start with scientific notation. Now, scientific notation is a way of writing very large numbers or very small numbers, and the format we use for scientific notation is a times 10 to the b power. I know that probably doesn't mean much to you right now, but it will start to make more sense as we work through some examples in the next slides. But b is going to tell you how many times your decimal place moved. When b is positive, it means that your decimal place moved to the left. When b is negative, it means your decimal place moved to the right. So let's try some examples. In this example, it's asking us to write 0.078 in scientific notation. Now let's start by taking a look at what needs to be our a term. Our a term is going to be all the numbers that are not 0 unless the 0 is trapped in between two other numbers. So for example, if we had 304, the 0 would stay there because 3 and 4 have to be the a value. So only one number can go on the left side of the decimal. All the other numbers will be on the right side for a. So in this case, we only have two numbers, so our decimal will go in between the 7 and the 8. So I'm going to bounce my number here. 1, 2, here's my new decimal will go. And I write my new number out, which is going to be 7.8 times 10. And in this case, we moved our decimal 2 times, and it's going to the right, so our exponent is going to be negative. I'm going to make this our superscript here, and I'll make this a little bit larger so you guys can see it. So our answer to this problem is 7.8 times 10 to the negative 2. Again, it's negative because we moved our decimal this way to the right. Had we moved our decimal to the left, it would have been a positive. All right, let's try another example. This one, we have 560,000, and we need to write that in scientific notation. So again, we only have two numbers that are not 0, the 5 and the 6, so our decimal will go in between the 5 and the 6. Okay, so we're going to bounce our decimal. 1, 2, 3, 4, 5. And there's where our new decimal goes. So our answer becomes 5.6 times 10, and this time we bounced 1, 2, 3, 4, 5. We bounced it 5 times, but this time we went to the left, so it's going to stay positive. We need to make that a superscript. And I'll make this a bigger. And here is our answer in scientific notation. 5.6 times 10 to the 5th power, because again, we bounced 1, 2, 3, 4, 5. All right, let's try another example. Now we're given 0.0009, and they're asking us to write that in scientific notation. First things first, we need to move our decimal so that only one number is in front of the decimal, or to the left. So this time it's going to go behind the 9. So we bounce 1, 2, 3, and 4. And so we write our new answer, which is 9 times 10. And this time it is 1, 2, 3, 4. It is negative because we are bouncing to the right. And we need to make this a superscript. There we go. We'll make it bigger so you can see it. Our answer is 9 times 10 to the negative 4th power. There we go. Notice that it's negative because we started with a really, really small number, or because we bounced our decimal to the right. And notice I don't have 9.0 because I don't need that 0. I can just leave it as 9 by itself. Okay, next example. We're given 45,790. And we are supposed to write that in scientific notation. Now this one's going to be a little different because we have a lot more numbers that are not 0. But remember, the only one number is allowed to go in front of the decimal or to the left of the decimal. So we're going to bounce our imaginary 0, which is behind it, or our imaginary decimal, which is behind the 0. And we're going to bounce it 1, 2, 3, 4, until that's the only one in front of the decimal. So it becomes 4.579 times 10, and we moved it 1, 2, 3, 4 times. And it's going to be positive because we moved it to the left. We need to make this a superscript. Oops, I made it a subscript by accident. We need to make this a superscript. There we go. I'll increase the size so you can see it nice and clear. And we'll highlight it in yellow. So our answer is 4.579 times 10 to the 4th power. All right, let's try let's try another one with 200. So we're writing 200 in scientific notation. So again, our decimal is imaginary behind our last 0. We bounce 1, 2 till we're behind the 2. There we go. We write our answer, which is 2 times 10 to the 2nd power. It is positive because we bounce to the left. And we need to make this a superscript. And then we can increase our size here. And now you can see nice and clear our answer is 2 times 10 to the 2nd power. All right. Now let's try it from from scientific notation to standard form. So they're giving us a scientific notation and we have to put it into the standard form. So it tells us right over here, 3.54 times 10 to the negative 4th. And I went ahead and wrote 3.54 here so that we can start our bouncing. And it's a little clearer for you to see. Because it is a negative number, we're going to make this a smaller number, which means we are going to bounce our decimal to the left. And we're going to bounce it 4 times because our exponent is 4. So we bounce 1, 2, 3, 4. And then we add our zeros in. 0. Gonna have to get them a little small. And another one. And 0. So we had to add 3 zeros. So our number becomes 0.123354. That was our original number. And to check that our answer is correct, we can look at our standard form and put it back into scientific notation to make sure they match. So if we were to move this, we would move it 1, 2, 3, 4, and it would be a negative 4. That matches. We're good to go. Let's try one more. They're giving us 6 times 10 to the 5th power, and they would like us to write it in standard form. So right now, our decimal is imaginary behind the 6, and we have to move it 5 places. Because our exponent is positive, we're going to make this an even larger number, or move our decimal to the right. So we bounce 1, 2, 3, 4, 5. And now we add our zeros. 0, 0, 0, 0, and 0. We added 5 zeros. So our answer is 6000000. And make sure we write our commas in the middle. Our new answer is 600,000. We'll make it a little larger for you. And we'll highlight it in yellow so you can see it nice and clear. Again, we can double check this by putting it back into scientific notation. If we were to put this back into scientific notation, we'd bounce 1, 2, 3, 4, 5. You'd have 5 as an exponent, which is what we have, so we are good to go. All right, next we're going to talk a little bit about precision and accuracy. Precision is the exactness of a measurement, and accuracy is a description of how close a measurement is to the true value of the quantity measured. So if we're thinking about this as darts, when you throw a dart, if you throw it on the bullseye, you are accurate because you're trying to get it to the actual value. If you throw it on the outside, on the right side, around the same area every time, then you are precise but not accurate. You can be both precise and accurate if you get all of your darts in the center around the bullseye, because then they're all around the same area, which makes you precise, and they're around the bullseye, which makes you accurate. So be understanding that those two terms do mean different things. All right, models and simulations. A model shows the structure of an object, system, or concept. A simulation is going to use a model to imitate a function or behavior or process of whatever the model represents. The purpose of models and simulations are to answer difficult questions, represent complex systems, test new ideas, and to make predictions. There are 3 main types of models: physical, mathematical, and conceptual. First, let's talk about physical models. Physical models are represents of the physical structure of an object or system. You guys are actually going to get to create a physical model by creating a physical model of a bridge. Now, physical models can be scale or life size. Scale means that it's going to be a lot smaller or a lot bigger than the real thing. For example, if you're going to make a DNA molecule is very, 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 very tiny, and you would not be able to see it. So you may enlarge it so that you can show the structure and the appearance of the DNA molecule. That would be a scale model because it's not the actual life-size model of DNA. The advantages of using a physical model is that it's easier and safer to work with. The disadvantages because it has its limitations because it does not always work like the real thing. Here are some great pictures of physical models. I again went ahead and wrote you the definition of the physical models. You have a model of a neighborhood and you have a model of a DNA molecule. All right. Mathematical models use different forms of data to represent how a system or process works. The advantage of mathematical models is they are powerful predictors. The disadvantages is because they can be oversimplified. And if I go ahead and give you an example, you'll see a graph here as a perfect representation of a mathematical model. And finally, you have a conceptual model. A conceptual model is a representation of how parts of a system are related or organized. The advantages of using a conceptual model is to identify patterns and similarities, also to represent processes that cannot be directly observed. The disadvantage is that it can lead to misconceptions or misunderstandings, and it can be oversimplified. Here's a great picture of a conceptual model. It's the rock cycle, which I'm sure you've seen before. The water cycle would also be a conceptual model. All right, that's all I have for you today. So until next time, I'll see ya. Thanks for watching.